right, so today we're going to talk about drawing covalent Lewis dot structures. With this, we are going to later learn how these structures can be applied to looking at a chart and determining what the shape and what the polarity of the molecule is. So these covalent structure drawings are going to help us represent those electrons shared in the covalent bonds. They're going to help us predict the shape of a molecule and determine polarity of that molecule as well. Note that these are much more complex than drawing ionic substances, so make sure that you are following the steps and make sure that you are doing the practice. All right, so I'm going to introduce to you the steps to drawing a Lewis structure for covalent compounds. I'm going to do this by using the example of water. So that seems to be a very common example that we've been using in this unit so far, but I think it fits really well with this as well. So the first thing you're going to do is count the total number of valence electrons in the molecule. So if my molecule is H2O, I'm going to look at my periodic table if I don't know these by heart, and I'm going to determine how many total valence electrons are in my molecule. So I know that I have 2 hydrogens, and each one of them is going to give me 1 valence electron. So I have 1 plus 1. And then I know that oxygen has 6 valence electrons. So in total, my molecule should have 8 electrons. Or 8 valence electrons, those bonding electrons. Then you're going to write the element symbol for each atom individually. You're going to basically be placing where these atoms are going in your molecule. And generally the least electronegative and or the singular element will go in the middle. So generally it's going to be our singular element. So if you have just one of a certain type of atom, you're going to put that in the middle. If there is not a way of determining that, we can also use that rule of generally our least electronegative will go in the middle. The only exception for that, so it says generally, only exception would be hydrogen. So hydrogen will not be in the middle of a covalent molecule. So I will draw mine here. So I have oxygen and it's going to be in the middle of 2 hydrogens. All right, so then I'm going to connect the outer elements to the central atom with a single bond, and that's going to be just a line. So this is going to represent a bond. All right, now each of these lines or this bond is going to represent 2 electrons, and those 2 electrons are coming from the 2 atoms that are involved in the bond. So if I'm thinking about this hydrogen right here, and then the oxygen, hydrogen, remember, has just 1 valence electron. Oxygen has 6. All right, so it's really representing these electrons here being shared. And that's what that line there is representing in my drawing. Then you're going to basically add electrons in pairs only so that each element in the structure has 8 electrons. Now, you should know that the exception to this octet rule, remember that everyone pretty much wants 8 to be like noble gases except for hydrogen and helium. So hydrogen is going to follow that duet rule, and it can only have 1 single bond and no lone pairs. So to basically make this complete, my hydrogens are good because they each have that single bond. They have 2 electrons. They're good with their duet rule. But my oxygen only, in my drawing right now, only has 4 electrons. So that's 2 electrons here and 2 here. So I'm going to have to add lone pairs in order to make it happy with 8 valence electrons. So I add those lone pairs. All right, so at this point, you're going to confirm the structure by making sure that the valence electrons in step 1 match the electrons drawn in my structure. So here is my structure here. I want to have 8 electrons when all is said and done in my picture. So I'm going to count them up now, and I'm just going to kind of put a little check mark by when I am counting. So I have 2 here, 4, 6, 8. So since this 8 electrons matches my 8 electrons that I should have, that means that I am done. So that is how you draw the Lewis structure for some simple compounds or molecules, covalent molecules. However, sometimes they're not going to match, and we're going to go into that in just a minute. But we're going to do some practice with this, do a couple more examples. All right, so a couple more examples just showing how this works. So hydrogen, remember, it only wants 2 electrons and it only has 1 electron, okay? So each one of these hydrogens here has 1 valence electron, but I have 2 hydrogens. So in all, I'm going to have 2 electrons. There's not going to be a middle one for this because it's only 2 atoms. So I have hydrogen next to hydrogen. I draw that single bond between them, and then I add lone pairs if I need to. Now, since each of these hydrogens can only have 1 bond, they're both good right now. I wouldn't add any more lone pairs on either one of them because they're fulfilling their duet rule. So my 2 electrons here in the bond matches the 2 electrons that I should have from step 1. For fluorine, so I once again have 2 fluorine atoms. So each fluorine, if you look at your periodic table, has 7 valence electrons. So 7 plus 7, since I have 2 of them, is going to be 14 electrons. So I need to have 14 electrons in my drawing. So I'm going to, once again, not have a central atom here, but I will put my fluorines next to each other. I will draw a line to represent the bond between them. And then I'm going to add lone pairs to make sure that everyone has their octet rule filled. So right now, this fluorine here only has 2 electrons in that bond or in that line that's going to the other fluorine. Remember that they're sharing. So this represents 2 for both of these fluorine atoms. So I have to add 6 more in pairs. So 1, 2, 3. So that's 6 more. And then I have to do the same thing to my other fluorine. So 2, 4, 6. All right, so now I have 8 electrons for both of my fluorines. Then we're going to add up the electrons in my drawing and make sure that they match the electrons that I had in step 1. So I have 2, 4, 6, 8, 10, 12, and then 14 in the bond. So just kind of recounting that, I have 2, 4, 6, 8, 10, 12, and then 14. So this matches, and that means that we're good. All right, CF4, so now we have a couple different elements. So first thing I'm going to do is add up my electrons, my valence electrons that I should have. So my carbon is going to have 4, and then I have 4 fluorines, which each have 7. So 4 times 7 is 28, 29, 30, 31, 32. So I'm going to have 32 electrons in this drawing. Now with this one, I do have a singular atom, and it is also the least electronegative. So remember that fluorine is the most electronegative element on the periodic table, so carbon is less electronegative. So carbon's going to go in the middle here. I'm going to put my fluorines around him. And then I'm going to draw bonds coming from my central atom. All right. At this point, I have to make sure that everyone is happy with their 8 valence electrons. So right now, carbon in all of these 4 bonds is going to have 8 electrons. So carbon, I'm not going to add any more valence electrons to, or lone pairs to. All right, the fluorines, though, only each have 2 electrons in those bonds, so I need to add 6 electrons as lone pairs to each of my fluorines. All right, and now everyone is good with their octet, and then I have to count up all of my electrons on my picture, so I'm just going to do this quickly, knowing that there are 2, 4, 6, 8 times 4, which I know is going to equal 32. So my electrons here in my picture, again, match, so that means that we are good. Sometimes you're not going to have them equal, and that's where some of these rule breakers that we're going to talk about are going to come in. So before you go on to rule breakers, I would just double check the number of valence electrons so that you added them up correctly. Make sure that you're fulfilling the octet and duet rules with their associating elements, and then double check the number of valence electrons on your drawing again. If it still doesn't match, that means that we're going to have to move on to rule breakers. So we'll describe how those work. All right, so our first rule breaker is going to be what we call cons. So if your molecule has bonds between carbon, oxygen, nitrogen, or sulfur in the structure, we might have to use double or triple bonds between the atoms. Sometimes this is just going to be trial and error to determine where the bonds belong. Just remember that when you are doing these, you have to make sure that each atom follows that octet or duet rule appropriately, and you have to recount the electrons in the structure each time you redo it to see if it matches the counted electrons from step 1. So the first one we're going to do is carbon dioxide. So just going off the rules that we did before, I know that you already know this is a rule breaker, but I'm just going to follow the steps. So I know that carbon is going to have 4 electrons, or valence electrons. Oxygen, each of them is going to have 6. So 4 plus 6 plus 6 is going to be 16 electrons. So carbon is going to go in the middle. It's our singular element. Our oxygen is going to go on the outside. And then I'm going to have to add electrons to make sure everyone has 8 to fulfill the octet rule. So right now oxygen only has 2, so 4, 6, 8. Carbon has 2, 4, so 6, 8. And then oxygen only has 2 over here, so 2, 4, 6, and then 8 would be in that bond. All right, so then I would count these up. I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So right now I have 20 electrons, which does not match with the 16 that I should have. So generally, if you have more electrons than you should, that means that you're going to have to draw a double or triple bond if you have one of these types of elements in your molecule. Okay, so generally when this happens, I like to obviously find the difference between how many I have and how many I need. So right now I have 20 electrons on my drawing. I only need 16. So it has worked out in the past when I've done this that when you are taking away electrons from what you need, it's good to take them away from the center atom first. All right, so right now I have 16 electrons. However, not everybody is fulfilling the octet rule. So looking at my diagram right now, I have 2, 4, 6, 8, 10, 12, 14, 16 electrons here. However, my carbon only has 4 electrons in those 2 single bonds that are bonded to oxygen. So what you can do is basically borrow a lone pair from those outer atoms to make a double bond. So if I do that, I'm going to basically borrow these electrons, so they're not completely going away like my ones from carbon did. And then I'm going to make a double bond between the carbons and the oxygen. All right, so right now, oxygen, if I'm just counting it up, oxygen has 2, 4, and then 6, 8 electrons. So oxygen's good. He's happy. Carbon has 2, 4, 6, 8 here. So carbon's happy with his 8. And then this oxygen, again, has 2, 4 in the bond, 6, 8. So that oxygen is happy. So now we used our 16 electrons, it matches, and everyone is happy with the octet rule. I find that this works the best to determine where our double bonds go or our triple bonds go. So let's do another example with that. So SO2, if I am just doing a normal drawing of a substance, my S is going to have 6 valence electrons, plus each of these oxygens will have 6 as well. So that's going to be 18 total electrons that I want in my drawing. So sulfur is my singular atom. It's going to go in the middle. My oxygens are going to go on the outside. So I'll draw my single bonds to it, And then I will draw the remaining electrons to make everyone happy with their octet. So 2, 4, 6, and then it's got 8 with that bond. Sulfur right now has 4, 2 in each bond, 6, 8, and then oxygen over here is the same as the guy over there. All right, so right now, if I count up all my electrons on oxygen, I have 2, 4, 6, and then 8, 10, 12, 14, 16, 18, 20. So here I have 20 electrons when I should have 18. So that tells me that I'm going to have to do something with double bonds. So as we did before, I'm going to remove a lone pair off of my center atom, all right, to give me that 18. However, now that I removed that lone pair, my sulfur is not happy, or it is not following that octet rule. It doesn't have the 8 that it wants. So I can borrow the outer atoms' lone pairs to make a double bond with sulfur. So keep in mind that these oxygens are the same element. So they're both oxygen. I need to make one double bond with my sulfur. And it doesn't really matter which oxygen I choose because they're exactly the same. So maybe the electrons are going to come off of this one over here, or they could have came off from the other one. And we'll talk about that in just a second. So I borrowed those electrons, those lone pairs from oxygen, to make a double bond with sulfur. So now my oxygen on the left has 2, 4, 6, 8 with that double bond. My sulfur has 2, 4 with that double bond, and then the lone pair is 6, and then the single bond is 8. And then this oxygen has 8 with its lone pairs and single bond. So now if I count them up, I have 2, 4, 6, 8, 10, 12, 14, 16, 18. So now it matches, so I have a correctly drawn Lewis structure. Okay, so sometimes when you are drawing double and triple bonds in the structure, they can be drawn multiple ways. So remember that we borrowed that lone pair, we took it from the oxygen to make that double bond with sulfur. I could have easily taken a lone pair from the other oxygen and made a double bond with that oxygen and sulfur. So it really didn't matter where those electrons came from to make the bond or the double bond, and we call that a resonance structure. So when you can make more than one structure, or it can be drawn multiple ways. So I could have drawn it like this, or I could have drawn it like this. And a way that we depict a resonance structure is to draw the Lewis structure so that all of our outer elements or outer atoms are going to have the absolute most lone pairs that they can. And then we're going to draw this dotted line to represent that the double bond could either go here or it could go here. So that dotted line is representing that I could have put my double bond with this oxygen, or I could have put that double bond with the other oxygen, and just also keeping in mind that if I do create a double bond, I am going to have to get rid of the respective lone pair from the oxygen. All right, sometimes if you have boron or beryllium as your center atom, they can have fewer than 8 valence electrons. So in the case of BCl3, so I know that boron is supposed to have 3 valence electrons, and each of these chlorines should have 7. So that is 21, 22, 23, 24 electrons total. All right, I'm going to put my boron in the middle. I'm going to put my chlorines all around it. Draw my singular bonds here, and then make everyone happy with their octet. So with chlorine, I have 2, 4, 6, 8, 10, 12, 14, 16, 18, and then all those chlorines are happy, but boron's not happy, so I'll add a lone pair there. So if I count up all my electrons here, I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So right now in this drawing, I have 26 electrons on my drawing, but I need to have 24. So as it says here, boron is one of those ones that can have less than 8 valence electrons. So it makes it really simple to remove that lone pair. And now I have 24. That equals what I should have from step 1. So you can only do that with boron or beryllium as a center atom. All right. And then another rule breaker is the expanded octet. So the last one was the condensed octet, and this is called the expanded octet. So if your central atom is located on in the 3rd to 7th energy level, it can have more than 8 electrons around it. So we're going to add those electrons in pairs around your center atom. So if I have something like PCl5, I would figure out how many electrons I need. Phosphorus is going to have 5, plus I'm going to do 5 times 7, so that's 40 altogether. I'll put my P in the middle since it's singular. I'll put my 5 chlorines around it with single bonds. And then I will make sure that everyone is good with their octet. Now, obviously, right away, phosphorus has 10 electrons in its bonds that it's connected to, and that is more than my octet rule allows. So just keep in mind that since it is located on the 3rd to 7th energy level, that is okay. But I'm going to make sure everyone else is good with their octet. So each of my chlorines is going to need 6 more electrons added as pairs. All right, so if I count all of these up, it looks like I have, let's see, so 2, 4, 6, 8 times 5, which is 40. All right, xenon and fluorine. So xenon, remember, is a noble gas, and usually we say that noble gases are not able to react with anything, but since fluorine is so electronegative, it can actually react with xenon. So now that we know that, I'm going to count up my valence electrons. So xenon is going to have 8 valence electrons, and then each of these fluorines is going to have 7. So if I add up 28 plus 8, I get 36 electrons that I'm dealing with. My xenon is going to go in the middle, and my fluorines will go around it. All right, I'll make my single bonds. Right now, xenon is good with its 8 electrons in those bonds. Fluorine, I'm going to have to add some electrons to each of those in pairs. All right, so 2, 4, 6, 8 times 4. Right now, all I have is 32 electrons on my drawing right here. I need to have 36. So we know that the central atom, xenon, is located on the 3rd to the 7th energy level, and it can hold actually more than 8 electrons around it. So since I have 4 more electrons that I need to put in my drawing, I'm going to put those on my center atom. So I'll put them on my xenon. Now, this drawing has 36 electrons, and it matches up with that number of electrons that I should have had from step 1. Okay, so the last thing we're going to talk about is drawing polyatomic ions. So polyatomic ions, remember, are ions that are involved in ionic compounds. However, the actual ion, the bonds in the ion, are going to be covalent. So we can draw them as covalent structures. One thing that we have to keep in mind that is these polyatomic ions do have a charge, and we have to account for that charge. So if I have a positive charge, it means that I have less electrons than a neutral amount would. And then if it's a negative charge, it means that I have more electrons than a neutral bond would. So with oxygen, I have 6 valence electrons, and my 1 hydrogen has 1 valence electron. Since I have a -1 charge, then that means that I have an extra electron. So now, instead of 7 electrons, I would add 1 more to get 8 electrons that would be in my drawing. So hydroxide, or OH-1, there is no singular or central atom, so I would just draw my O next to my H. I'd put a bond in between it, and then I would make sure that everyone's duet and octet rules are filled. So with oxygen, not happy right now, it needs to have 8, it only has 2 in that bond, so I would add 6 more in lone pairs. And then hydrogen has the 2 that it's happy with, so hydrogen does not want any lone pairs. So right now in my drawing, I have 2, 4, 6 around my oxygen, and then I have 8 in that bond between oxygen and hydrogen. So that matches my 8 electrons that I should have. The last thing, as we do with anything that we're doing stuff with ions, I need to draw brackets around my Lewis structure, and then I have to put the charge on here. So just like we do with most of the things that we draw with ions, you have to make sure that you have brackets and then the charge of the ion on the outside. If you have any questions about any of these drawings, make sure that you are asking. We're going to do a lot of practice with it. We're going to be working with models, doing some computer activities, and hopefully you'll be a pro at drawing ions and covalent molecules at the end of it.